projects such as the new Christmas lights for their hometown's shopping mall, a stunning entry for the Sorossi Pavilion competition that was on show at the AA in the last term, and most recently an ornamental brick facade for a winery in Switzerland that was produced entirely by robot. They are both graduates of the ETH Zurich, and before setting up their office, Matthias was teaching there with Greg Lynn and Marc Angelil, while Fabio founded the art collective eToy. Matthias and Fabio's combined backgrounds have resulted in a practice that finds creative freedom in the manipulation of digital data, a practice that favors the discovery of the unexpected and the invention of the new over simple optimization. In Gramazio Kohler's world, customers design their own tables via mobile phone, Christmas lights become kilometer-long LED screens, and architecture students program robots. Since 2005, Fabio and Matthias are assistant professors of architecture and digital fabrication at the architecture department of the ETH Zurich. It is there that they are undertaking their most radical work to date. With the help of their students and an industrial robot, they are reinventing design processes that are at once fully digitized yet firmly rooted in the realities of building. One of the most challenging tasks in contemporary architecture is the scaling up of mass customization technology to building construction. It is inspiring to see how Fabio and Matthias are facing this challenge head-on and produce working prototypes using affordable and tested materials to stunning and, dare I say, ornamental effect. It seems pertinent that this work is being produced at the ETH, the home of Gottfried Semper, who in 1851 gave us the ornamental theory of the Wand als Gewand, or the wall as garment, as woven textile. It is also at the ETH, the natural habitat of the Swiss box, where 140 years after Semper, I first met Fabio. We both just finished our first year as architecture students designing housing within a given 3-meter cubic grid. No deviations were allowed, the 90-degree angle ruled supreme. I soon fled to the AA, but Fabio persisted, and it has only taken him 16 years to smuggle the other 359 angles into the ETH's vocabulary. Now that is a true achievement. Please join me in welcoming Matthias Kohler and Fabio Gramazio.
Well, dear Oliver, thanks a lot for that welcome. We're very happy to quickly get that fixed. Very happy to be able to present our works here at the AA. It's an honor for us. It's a different context. It's definitely not the 90-degree angle. We have seen that already in several displays and from other contexts that we have to the school. And I think, though, the kind of exchange between the AA and TTH could be particularly interesting because of the constructive issues that I get a sense of, like when I go down to the digital prototyping lab, and also in the handmade workshops, kind of the constructive culture that seems to be around here in the school, and also based, at least on the model making scale, but it goes up to prototyping scale from what I've seen also outside. And for us, it's this maybe a partial issue here is a central issue in our research. We often kind of call this digital materiality, the coming together of digital data and physical materiality in an architectural construction. We think that the physicality of architecture is one is kind of a pre-requirement of architecture. So looking at that on the one hand and taking the digital design tools as we all know them today as a second given and pre-requirement, and the fact that we as architects, when drawing a CAD line, are already producers of data, if we kind of merge these two worlds, it is interesting to see what actually comes out of this real merging. So taking the physical prerequisite and the digital as kind of two bases of our work today. So it's not so much about saying where this is going, but taking these two fundamentals as kind of as a base and starting the research from there. So that's kind of our look onto the world. And to give you an idea how we actually perceive this, or how we actually pursued this research, we're going to show you 4 office projects. Most of them are older projects, which are also to some extent experiments, to give you an idea how we actually came up with the questions rather than the answers. Those kind of office project then led us also, or gave us also the opportunity to start the research at the ETH. Oliver has already told you about that, and where we do this work with this robot, which is also actually posing out more questions. And basically, we think it's to all architects to start thinking about the answers. Of course, we do that as well, but we're not in the position right now to actually present them as a kind of complete, wrapped-up package.
Okay, so we'll jump in this lecture by showing you an older project. It's not a building; it's a piece of furniture. It's called M-Table, and it's 6 years old by now. M-Table is a table that can be designed on a mobile phone. This is meanwhile an old mobile phone, but it's a complete computer. And it's a computer that is not, at this time and now, it's not perceived anymore as a piece of technology, but it's much more a personal device, it's a gadget. It's like a watch. You don't think about your watch as a technological accessoire, but it can compute. Here we have a short video that shows how this thing worked. It's a very simple design principle. The user can manipulate the surface by setting pressure points, and then with the joystick it sets a pressure. This deforms the lower surface of the table, and if the pressure is strong enough, it generates holes. Then of course the user, as normal, can choose a color, can set the dimensions of the table, and he can look at it three-dimensionally, but in a very, very low resolution mode. So he has very few actions he can take in this system, and he has a very rough feedback of the whole thing. When he's satisfied with the design, I mean, it's not a professional manipulating this design system, of course. Then he pushes on a button, and he sends the data or the design to the server. And this is what is transmitted. It's very few data. Partially, it's readable, human readable. So you have an authorship. This is the first thing. It's the most important thing. Then you have a color. Then you have dimensions defining the kind of bounding box. And then the other set of numbers, it's just the position of these pressure points and the strength of the force applied. With the design algorithm, of course, we can generate a surface out of this little data, and this data now can be transmitted to a machine that produces this design. Here you see the first prototype we built when we had this idea, and we started to work on this principle. And you see, it generates an object that is somehow familiar. It's a table. I mean, we choose the table because it's something everybody knows how it should look, how it should behave, and so on. But, and this is an interesting point, or the point that fascinated us back at this time and still motivates us to show this project, this old project, it allows the user to enter by parametric design I would say the exclusive domain of the designer. So it's the domain of form, of shape. And it's not just limited on, say, exterior consequences on shape, but it's really attacking functionality. I mean, if you allow the user that is not trained or educated to decide if he wants to put holes on his table, what is completely anti-functional, then you give him a big freedom. This slide shows how the principle works. So on one side you have the realms of data, then you have the device with the software. This is the most important part. There were design decisions are done by us. This is the whole point. I will explain it later. And the other side, you have the production steps that are needed to, in the end, have a wonderful, high-definition, physical, sensual piece of furniture. Now, this project was, and this was very important to us, here is the webpage where you could order it, was not meant to be a business case or a commercial success, of course, but it was completely real. So we produced 10, 11 pieces, and they were designed and ordered by people. They were pretty expensive, so it was not a kind of a game, of a joke. It was expensive. And those people here, you see a couple of pieces, had to kind of decide at a certain point that they would take responsibility for their design. And this, accompanying this process, was a very exciting experience, of course. Because I mean, you could feel how those people got insecure in the process, and at the same time, this picture shows it. This project that has a kind of an ironic undertone deals with the issue of freedom on one side, and what you see on this picture, the control that still is there by us, by the architect, by the designer. Even though we are not designing, controlling, defining the form anymore, even if we open up the system, we are still authors of the system. So we design a process, and the outcome of the process, even though every single design, those are not built design, is completely different. They are unique. They all belong to a design root, and this design root is very strong. So just a question of, and this was then the outcome for us of this process. It's a question of finding out where our intervention, what level, on a systemic level, can lead to a strong design, and where it's just random.
As a second experiment, which we conducted on bringing data and physical matter directly together, it's called the interference cube. It's basically just a concrete cube, rectangular of course, measuring 2.3 meters on its edges, weighing 7 tons. So that's kind of the physical and material part. And on the other hand, basically it's a program which designs the inner surface of this cube. And what we conducted was the kind of research question that we asked is, if we work in the Cartesian computer space XYZ, why are we still kind of tempted to work in plans and sections, and especially if we look at kind of ornamental questions, why are we drawing kind of textures or manipulations of surfaces onto the planar surfaces, and then somehow trying to fix how this information goes around the corners. So what we are looking at is actually at a spatial field. So what you see here is a turbulence field in Maya. Most of you probably know this. And so as I speak to you, we have sound waves which go out in the space. So we looked at a real volumetric kind of set of data, and then said, okay, we read the information for these surfaces out of that volumetric data. So the the ornament or the information, the content, so to say, is spatial, but the geometry it is placed upon is planar. So the result is here you see an early rendering. Is this kind of this edge is actually a mixture of this continuous information, like the sound waves when I'm speaking, or if you take an onion, for example. So it's continuous information within, and then if you cut the onion, if you cut out a cube of the onion, then actually by the cutting out you get kind of a discontinuity of information. So there's kind of a new aesthetic coming from that. You see here these 5 surfaces, inner surfaces of this cube, where you have these kind of ruptures in the edges, but the information on the plane is still continuous. We produced it. It was 8 millimeter deep milling, so a very shallow milling. And this slide shows now the coming together of these 2 realities: the high resolution data space and the concrete. And what it produces physically was then interesting, because suddenly, I mean, where does this product belong to? Is it a physical product? Is it something you know of, or is it a data product? And that comes back to the question I said in the beginning, or this word digital materiality. What are we actually looking at here? Is this computer space? Is this physical? What is it? And this is the question which starts to interest us. So, like, although it's just a very, very simple, shallow texture, there's nothing very special. I mean, all the people that saw this, they actually had to touch it. So it's interesting. People start to touch architecture again. It's transportation. An edge detail. Here you see the continuity and the rupture at the same time.
So the third project is a pavilion we built in 2002 for the Swiss National Exhibition. This was a so-called Arte Plage, a kind of bridge in the sea by Coop Himmelblau, and we had a pavilion. You'll see a view of it, the plan, the section. I will not discuss this. I want to go, you see, it's a very simple wooden construction. It has big holes in the platform, so it's completely closed. The space relates to the water, to the sea underneath. What I want to show you are the facades, 2 facades, the external facade, and afterward the internal facade. We treated them as continuous kind of surfaces. And we got, because of course this is a real building, but as an exhibition building it has to last 6 months. So you have a very large freedom on the client side to do experiments. So we got interested into this question, with which kind of material, with what kind of technology, and with which kind of manipulation of those construction techniques we could do this architecture that in itself is completely banal. It has just to be a black box for an exhibition with the usual multimedia shows. We treated we found a material, polyurethane, that has a very interesting property of being very robust. So you use it to insulate. At the same time, you can stretch it. It's soft. So what we did was to insulate the whole pavilion from the exterior with soft insulation material, and then to spray this coat, this 3 millimeter of polyurethane directly on the facade. The advantage, and you see it here in this picture, the advantage is that you can really forget about all the traditional detailing you need in a building. So normally you need to connect the roof to the wall and the wall to the ground and so on. And here we just sprayed all over. The result was a very interesting building volume. The shape it's defined, is hard, looks like it speaks about precision. At the same time, you feel that with the material something is strange. So you have this perfection and this imperfection at the same time kind of overlaid. And if you approach the building, and this was our interest in this space, so this large thing, just occupying space, people around wondering what's inside. So we operated with these large benches where people could take a rest. At the same time, discover or touch this unknown materiality that normally you think at the building as a hard, resistant thing, not as a surface you can push in for 10 centimeters. This worked very well. The other story is the reverse of this facade. In the interior, we needed an acoustic treatment for usual acoustic reverberation problems. So you have one large room, 700 square meters, 300 people at the same time visiting it. The normal solution would have been to build it and then to take some absorbing panels and to find out how much square meters you need to adjust your reverberation time, and then mount it, buy and mount it. We said, no, let's look at what we have. We have a cheap wood structure. We have wood panels on it. And then on the other side, on the exterior, we have insulation. Insulation is soft. So let's drill holes through the structure, so through the wood panels, and let's open up a certain amount of this insulation material we have anyhow to the interior of the space. The next thought, of course, was, okay, if you have this freedom, we need so many square meters of insulation, and we have a machine that can drill, so let's treat the whole thing like in the exterior, so the 5 facades homogeneously. And so we took the technique of the interference cube we have shown you before, and created a pattern, a continuous pattern that would be composed out of these holes. Here you see images of the very nice images, but it's the construction site, of course, then it was covered. And our problem, and we are showing it to you for this reason, was that not so much the idea or the strategy was of interest to us, but when we got or started to get to ask contractors for a price for this idea, we very soon got aware that this would be way too expensive. So a normal acoustic material, even though it's more material and more work and so on, would have been cheaper. So we asked ourselves why. We talked with the contractor, and we found out with astonishment that the money was not going into the machine doing something, but 3/4 of the sum he needed to do the job was translating our design data into data that his machine would understood. So a completely stupid interface job. So we had the idea, a very simple idea, how would it be if we are the authors of the data, we produce this data on our software, we control it, we know it, why shouldn't we write G-code directly out of our design data? And here you see this G-code. It's very simple. I mean, you can read it. It's just a couple of very simple commands. This mill understands, so go to this XY coordinate, and then drill. So you have a Z movement, and then you have a couple of other very simple control parameters, like how fast the mill should turn, and so on and so on. By convincing the contractor to use our data, of course this wasn't simple. It only worked because we knew him and he trusted us. I mean, you have to imagine this is a large scale machine, costs a million Swiss francs. This is, I don't know, 400,000 pounds. And if you have one wrong number in there, then it's fucked. Yeah, it's broken because it's not meant to be. I mean, all the software packages and so on are just controlling this. So for him, giving the control of his machine to people that do not know, that are not part of his business, was a kind of crazy action. But by doing it this way, we're able to produce this, kind of integrate this further functional functionality into the material we already had just by producing data for the price of painting the square meter. So it was ridiculous because he just got files from us. He had to change the wood plates on his machine, and he was done with the job. So this made us aware that on one hand we have, as architects, if we recognize this point, an enormous chance to really deepen our control, creative control into the process of making architecture, and on the other hand that there is a lot of work needed or experiments that have to be done, not just on the level of material of architecture, but on the level of processes, because this was done because we convinced him to shift the interface, traditional interface between us and him. But for this operation, there is no contract. I mean, you cannot. How would you in the everyday construction business deal with such a situation? He owns the machine, and I work on his machine. And what happens if something goes wrong? So it's a situation, contractual situation, legal situation that is not defined. So it has to be redefined.
Okay, the next project it's called the World's Largest Timepiece. It's a Christmas illumination, a competition we won 2003, and a project we completed 2 years ago for the Bahnhofstrasse Zürich. Maybe some of you are familiar with it. It's basically kind of the central shopping street in Zurich, and here you see a plan view of the site. It's a very exciting site because it's 1.1 kilometer long, so it's an interesting project. It has an urban scale to it, yet in the same time it's basically just a Christmas illumination. What you see here is actually our main design proposal. We during the competition we of course had the plan, this plan on the wall, and we actually became fond of the geometry of the street itself, and the fact that most people that know the Bahnhofstrasse, they think actually it's a straight street which goes from the station, which you see to your left, to the lake of Zurich, which would be on your right hand side. But in fact it's not. It has these two slight bends, and we basically chose to just accentuate this situation of this actually line which is not straight. Here you see a view of the completed installation. It is kind of a ribbon of light which hangs. It is 8 meter high and is 1.1 kilometer long. It's composed out of 275 lighting elements, and these tubes hang in a height of about 14 meters at the lower base. And so one part of the project is kind of this hanging ribbon of light, and the other part of the project is actually what is happening on this ribbon of light, because of course it changes. So it's a project which is actually a project in time. So we had to compose and work on two levels. On the one hand with this design in time, and on the other hand with the physical constraints of getting up light in an economical way and in a structurally feasible way in this height in the middle of the streetscape. We actually worked together with Arup on this project because it was quite difficult, as you can imagine. All the buildings are different along the Bahnhofstrasse, to actually optimize the cable structure so that we could have this ribbon of light as a continuous structure. You imagine there are places and spaces, open spaces where you have no buildings to attach to, and so on. So that was a very complicated project actually, and hard to achieve. But I'm not going to go into further details of this. Instead, I would like to show you how we actually built and conceived this lighting element. You see a close-up view of some of the lighting elements during testing before they were actually hung. We had to find, or let me quickly tell you the problem which we are facing. On one hand, we have a lighting element. It is 7 meters long, so it's about from here to you, probably a bit longer. It's a very long element. It's just 15 centimeters thick. So structurally, it needed to be stable. On the one hand, there's a lot of wind loads also up there which need to be taken care of. That's on the one hand. On the other hand, we wanted a light diffuser because all we wanted up there was light. We didn't want basically material or shadows on these lighting elements. So our first tries was actually working with an aluminium core structure and then covering the structure with a light diffuser. Different materials were looked at. And later we found out, well, this actually aluminium core, beside the weight problem, we had the problem that it would actually start to shade a lot of the light, because also the ends would have to be to become quite thick, so they could actually withstand all these forces that we had up there. So then we also have the question, well, there must be material which actually combines both of the properties that we needed. So light diffuser on the one hand, and structural stability on the other hand. What we found was this production method called filament winding. So basically what you see here is a metal core tube onto which glass fibers are spun. These glass fibers go through a resin bath, and let's stay on this. Go through a resin bath, and this tube is actually filled up with these fibers. The way you actually spin these fibers onto this core influences in a very direct way the way light is emitted or diffused through the structure on the one hand, and on the other hand it directly changes the stability of this tube. So if I have this structure or this structure, will completely change on multiple levels. So as you see, we have done some simulations and looked at these structures to finally come up with quite a simple solution, but it took us about 25 prototypes to actually come there. Here you see the final structure of the hollow tube. Where it is darker, the material actually gets very thin. Basically, there you just have resin. This makes this tube become quite brilliant in the night. And where here in the image it's more of this brighter green, is where the material actually thickens up, and that's actually where the forces will run through the tube. And also the angle will tell you whether it's stable in the cross section or in the length section. So just to give you an idea of how this is produced. So that's also basically a large CNC controlled machine. So it's also something which depends on the data it's fed with and on the material, of course, it is fed with. You see the glass fibers into the resin bath and onto the tube and on the back. What is interesting about this kind of fabrication procedure is that you actually add material. We're going to come back to this later. You add material so that it fulfills the functions that you actually want to have incorporated in the structure that you build. So on a very basic level, you start to decide what properties you want to have in a building element. The lighting elements taken out of the oven where it was hardened. This fabrication procedure has not been used for lighting elements, as far as we know. Before, basically it's technical elements which are being produced that way. So elements which should not conduct electricity, but need to be of high stability. You see the gluing of the head part. This part will include the kind of local control for the lighting element. The gluing is the standard technique. In this rounds you cannot screw this because it will break. So here, just to give you a kind of a close-up view of these lighting elements, here you see again these thinner lines which actually make the lighting element kind of brilliant, and the thicker parts which actually are responsible for the structural stability. So after this excursus, just to give you the other side of the story, that's basically the design issue. We programmed the software in our office. It's called the Christmas Generator, and it produces 320 hours of Christmas every year. Because how do you design 320 hours of Christmas time? This is the time which each year the installation is running. So how do you design this? If you produce a video, it's kind of hard. Everyone who has done video editing know how much time it takes to come up with a decent video work for only a couple of seconds or minutes. So from the beginning on, we decided to actually program software and do the whole design algorithmically. I'm not going to go into details, but here you get an idea. Maybe you see some formal details which remind you of Interference Cube and other projects, basically on how the design was programmed. It's also using force fields, which we custom programmed this time, not using any other software framework. This is all a C++ code, because it needed to run. It needs to run real time, so it produces images constantly when it's running the software. You see some other example. And to give you an idea how this looks in space, I'll show you part of the opening 2 years ago.
So now we move to the second part of the lecture, when the robot comes in. So till 2005, so 2.5 years ago, we had, as you've seen, nothing to do with robots. We were just doing architecture, experimenting with machines that were out there, available to, more or less available, and very available if you took chance or they had the courage to directly manipulate data. So to understand what they were good for, where you could really take an advantage by using them. When we got the position, as I said, in 2.5 years ago, we were asked in the first interviews by the board of the school at ETH, you get a position, then you have to deal for start money and structure and all of this. And of course, even though we were not prepared for this question, it was pretty stupid from our side. One of the first question was, what kind of a machine would you need? What would you buy? And this was a logical question, because ETH, as a technical high school, and being the whole discussion about budgets, about money, we had to define it. The first time we were confronted with, we said, okay, the last 5, 6 years we work with machines out there, and we do not need any particular machine. Then the question came a second time, and then we got kind of obliged, but also interested in the issue. And we started to look at what kind of machines were available out there. And by analyzing the market, we found out that all the machines we had used till this point were specialized machines. So machines that are built to do a certain thing. A mill can can mill very fast, very good, very at a degree of perfection, let's say a tenth of a millimeter that it would not achieve otherwise, but it can just mill. Then we found the robot, the industrial robot, being a machine. This is out there on the market. It's an industry standard since I would say 20 years now. It was invented in the 50s. It has a kind of a mythology or attached to it because it's called robot, and when we humans hear about robots, we start to think about intelligent machines and so on. This is not the case at all. This robot is completely stupid. It's just 6 motors that move, that can be controlled by data. At the same time, the machine is cheap. This is a question of numbers. There are 1 million of those machines installed worldwide by now. They are all the same, more or less. They are very stable. This machine does not break, cannot allow to break, because normally they work in the automotive industry, for example. You have thousands of them working, coordinating the making of one car. If one of them breaks down, then the whole thing is stopped. This creates an enormous damage. So all the engineering went into making those machines not intelligent, but robust, stable. But the most interesting point that fascinated us was the fact that the machine is completely generic, opposed to the specialized machine you saw before, the filament winding machine or the mill. This is generic. It's like a PC. We call it the PC of fabrication, because it's not just able to read data. You can feed it with data that controls it and moves some engines, motors, but it doesn't have a scope. It just can go like our arm somewhere in space and do something. And when you buy the machine, it comes without any tool. So it's completely up to you what you will manipulate or do in space. This was the reason in the end why we choose to buy it, because it would be, we hoped, and by now we are convinced it every day challenges us. So it kind of obliges us to keep our research completely open. We can jump from one thing to another just by changing the tool and the data that controls the robot. So when we, of course, this was more complex than we thought, and the machine came a bit late, and we had the studio running fall 2005, and so the kind of start with this machine was extremely simple. We said, what is simple to implement on this machine? It's drilling holes, not milling or doing complex paths, just drilling a hole. Plus, it's a very simple manipulation. Students can understand. Students can practice it by hand too. Everybody knows use the drilling machine. Someone has this direct experience about what kind of data is involved in the game. It's just a position, then a vector, and then you move in and move out. That's it. But architecturally, even though this element, the whole, is known and formally very, very simple, it has a complexity as soon as you start to postulate two things. So we will not use 10 holes. Let's take the hole as a architectural opening, a window. We will not use 10 of them, or 5 or 50. An amount, the quantity we are trained to manipulate, to design with. But let's take 2,000, for a simple reason that the machine doesn't make any difference if it drills 10 holes or 2,000. And then let's make another thing. So you have the problem of distribution, the first problem. That's this one. And the second assumption is the machine has no difficulty to go just somewhere in space and drill a hole, but it can also drill the hole in following a certain vector, and all those vectors do not need to be the same at all. So by doing this, we were confronting the students with the, I would say, most fundamental issue of the relationship between machines and humans. Because the machine, this machine particularly, is stupid, so doesn't have any sense of the environment, doesn't see anything, doesn't feel anything, doesn't think. It has no intelligence as we understand it. It's like software. Software has no intelligence. We bring in the intelligence by designing software. Back to the M-table project. But the machine can do things we would never do for a matter of time. I mean, we can do this, but it would take us 5 years. The iteration time that we can implement with logic here, if we do it by hand, takes us 5 years. So it's not impossible, but not very plausible, not very likable that somebody would do it. The outcome of this very simple semester was abstract, scale-less architectural volumes with 2,000 holes in them, and for each one of them a strategy, an algorithmic strategy on how, where to place them and how to direct them, where the holes should look at. And what you see here, this is just one of those 9 works we had at the end of the semester. Shows how powerful this very simple manipulation direction is. If you look at this corner and you look at it in the second image, it's just the information this group of holes has about where to look at that suddenly generates spatially. Of course, here now it's more dramatic because you have light in it just to see it, but you could imagine if you are at a certain position in the volume and you look at this corner, it dissolves in nothing. It gets two-dimensional. Here you have a further surface that doesn't exist geometrically, that is just generated through the common orientation of those holes. This is a spectrum of works we get. Okay, then this was kind of a first approach to the topic for us to find out what we could do with students, where the potential really is. After having done this, we were interested in translating. This is the technique we now apply in a standard manner. So we do first a studio that analyzes some phenomena and a possible interaction between man, us, and the machine. When I say machine, I mean the robot and the computer too. And in a second following studio, we examinate how or what would happen, what happens if we take this hypothesis and we build it one-to-one with real material. So we said we want to produce an architectural element. Architectural element, I mean something that can be prefabricated, so this 3 by 2 meters, for example, in concrete. And then we had with the students to kind of engage in very basic construction problem, because you know how a concrete wall looks like, feels like, smells like. You know how it's done with formwork, with reinforcements, steel reinforcements in it. And suddenly here you have to question the whole thing. First, how do you bring the information? This information, the same problem you have in the model, you have in one-to-one scale. So you have first to bring the information about the holes in the material. In this case, you bring it in the formwork. Next, you take standard plastic pipes and you stick them into the holes. By doing this, you create stability, so kind of interlock the two formwork, the panels of the formwork. Then the third problem is, if you look at this structure, it's not thinkable anymore to take a straight reinforcement and to put it in there. I mean, if you would do this, you could calculate it, but the eye would see it, that there is some kind of regular structure interfering. So we had to use, and this is nice, and the facility we have there, we are neighbors of structural and material engineers, and so we started collaboration, finding out what kind of materials we could use to do this, and they came up with a self-compacting concrete with steel fiber reinforcement that they were developing, testing, so we put it in there, and it worked very well. This is the outcome. What you see here is, or what is interesting is still this overlapping between two logics that you know both of them. Since 10 years working with software on computers, you know this is static, but you haven't seen them in the material. On the other way around, you know the material, but normally it's not transparent. And if it's transparent, it's regular. It's not kind of controlling where you can look through. It's not playing around with your position or position of the light. So there is a whole new kind of spectrum of architectural possibilities. I'm not only of effects. I mean, if you see the image, you would say nice effect, it's decoration. But if you move around it, you start to feel how deeply architectural, spatial those kind of phenomena are. And if you get control over them, and you can use them not in a repetition way or randomly because you do not know what comes out, then it's a very interesting mean of expression. So then we went on. I will go over this project very quickly because we are short in time. We extended this investigation on the architectural opening and on the large number of architectural opening by opening up the formally very constrained object of the whole, being a circle with a direction, and started to work with other ways of distribution of cells. This was a Voronoi diagram, for example, trying to take out material till the point that just a screen is left. And the screen is another thing we know architecturally what a screen is, but this kind of screens here, just by the way, I mean, it's a very simple logic. I mean, it's two Voronoi diagrams that are not placed in the middle, so it's not two-dimensionally. There are two different placed on both two sides, and students wrote algorithms to manipulate them separately, and then the third step was the control of how the robot goes through the material and mills. And what you see here, all this find an image where it's clear. This always front and back side. What you see here, this very complex plastic shape in the shaft that is informed by the direction, by the shift between the two informations. This is not designed. I mean, it's not described geometrically. This would be madness, data madness. But it's just the coming together of these two milling paths on the two sides, and then the shift. I mean, it's called spin, just by not connecting the two nearest points of the two sides of the path, but by shifting this a bit, then you get this kind of forms. And this was the first time you will see it in the last project that we are doing right now, where we deal with foam. This was a point when we found out that making things in this domain is extremely important, because it's just when you think that you cannot describe, that you cannot simulate, that you cannot render, that you cannot draw, you have to make them to find out and kind of reverse engineer why something happens, and then reintegrate this in your design system. They are extremely intriguing products, even though, I mean, this is just mock-ups, so it's styrofoam, so it doesn't have like the concrete walls any architectural impact.
Okay, we're going to move on to a couple of projects which are revolve around our main kind of research focus on the fabrication side. As you see, there are multiple research which kind of overlap. There's architectural research, there is computational design research, there's fabrication research. So from the fabrication side, we are actually interested in additive fabrication. Why is that? I mean, you see very little architectural production on a one-to-one scale, which is actually made subtractively. Well, there's formative procedures of making things, but actually adding material to start to enclose space or define space is a very architectural, basically standard procedure. All we see around us is basically done this way. So this very simple line of thinking is actually what interests us, and is also one of the reasons why we actually decided for the robot, because there is no machine out there which adds us material in one-to-one scale. So in order to start these experiments in this direction, we set up a course, it's what's called the programmed wall, where we actually came back to kind of one of the most well-known additive building elements. It's the brick. And we ask ourselves, okay, now what happens, or we ask the students, what happens if you build a brick wall by designing it on a computer and building it with the robot? So first the students, they made hand tests in order to figure out the parameters, because we're still working in physical space and not in kind of virtual space. And then they actually programmed their wall. So they did not do a design in any CAD software, but basically, I mean, if you think of bricklaying, it's like a very simple program. You start with one brick, and then you lay another brick always on the side of the last one. Then you go to the next row. So basically you have two loops. You see there, vertical loop, horizontal loop, about in a third of the script. So basically you have two loops, two nested loops within each other. Although the students were not fit in programming, I don't know how it is here at the AA, but at ETH basically students don't program. They actually could follow this very simple logic and idea. They were running the program, they got a simple wall, and then they could start to alter it and change it. So this is one design which actually just works with the rotation of bricks. Here you see a plan view of it. In parallel to the students, our team actually had to make the robot fit in order to build this wall. So we changed the tool to a gripper, and we added some parts to the gripper so that it could actually hold the bricks. And you see the first wall that the robot built. A bit clumsy, it's his first time. And here you see the results. These were these first three walls that were designed for the robot and directly programmed. And what was intriguing for us was that well, we all know what we can do with bricks, and we think we have seen it all. But now actually bringing it together with these digital means, but not only the means, but also conceptually opening up the way we architects actually work with those means, starts to really produce new artifacts. And that was really interesting for us to see that, okay, these merging of data and physical matter can actually produce new architectures at the very base level. What is interesting, as in the projects we've seen before, is that the depth of the material is starting to come out to actually show, because we can manipulate it. So we don't automatically have to kind of work on surfaces and work with surfaces, which we are very much used to do nowadays. On the one hand, because the building industry moved to this economic reality of how architecture is being produced, and on the other hand, because software also works on surface paradigms. So it's also interesting to kind of question those basic paradigms we're working with currently. Another interesting thing is that you start to reappreciate material through working with digital means, because you see material in another way than you've seen it before. We went on with this research. I'm going to be a bit quick here. We actually asked ourselves, okay, a mason can lift maybe 25 kilos, so of course the brick is made for a mason. A robot, or our robot, can lift 110 kilos. So actually it could be much more economic to actually work with large volumes. Then we said, well, we're working with large volumes. Our research is not about economics, so how do we deal with large volumes versus small volumes? And in the semester resolution wall, we asked this question to the students, and we actually worked with 4 different sizes of volumes, the smallest volume being a 5 by 5 by 5 centimeter generic cube, and the largest volume being a 40 by 40 by 40 centimeter cube. So the largest one being made for the robot, the smallest one almost too small for the robot. So how do we deal with this? What is special, of course, building the same wall with the large bricks takes you only 512th of the time than building it with the small brick. So it's a very basic kind of paradigms of additive building. So we try to go further with that. This is the material. It's porous concrete stone. We had to change the physical side, the tooling side. This is an adapted gripper, which kind of actually sticks into the material and then pressures it apart to hold the bricks. And there's a small vacuum gripper on the bottom to hold the very smallest of these modules. Here you see the building of a wall, which now has different resolutions, physical resolutions in it. This is where the first project has also had like internal like voids embedded into these volumes. For time reasons, I'm not going to go into design details here, but this one, for example, was optimized using genetic algorithms so that it would be fit on the overlaps of the stones. Maybe you see the first design on the top would be very unfit, so basically the stones would fall apart, and then you have an interlocking within the same exterior wall shape produced by by the different volumes, which then by itself produces an aesthetic, which is also quite interesting to look at. Also, you could think of these products now in a different scale. So basically we're focused on the one-to-one, but there's of course always room to think about other things. So now we have the possibility, I'm just quickly going to move on, to actually realize a project with the brick building technique. And this project is an extension to Winery in Flash. It's an architecture project by Beat and de Platzes architects. So the design is not by us of the building. It probably would look different. But we had the really great opportunity to, because Beat de Platzes is the dean of the ETH, so he was at our final review and he saw what we did with the brick walls. So, and he was asking us, well, this building, it's actually already halfway built, but they had the idea to actually bring bricks and turn them on the side so that through the holes you get filtered light into this winery extension, so that you still have working light but you don't have hard temperature changes by the sun. So since our structures were actually open and not closed walls, we said, of course, we're interested in joining in this project. And we realized all that you see now, we realized actually in, what was it, 3-4 months, basically from the first idea to the finished building of and design of the facade. So we had to teach the robot the gluing of the bricks, because these are like 400 square meters of facade. So what has been done by hand by the students with the first walls was not very practical here anymore. You imagine we work with the principle of rotating stones. You imagine, since every stone can be rotated individually, and then you put a third stone in the middle of two individually rotated stones, which is also, the third stone is also individually rotated. Of course, every gluing path on every stone is individual. It's no problem for the computer, but you wouldn't want to do it otherwise. So what is very kind of self-evident and natural with the computer would be horror for men to do. We did testing for the gluing, and here you see we kind of optimized the fabrication process. We do four walls at a time. So this comes very close to kind of 3D printing in 1-to-1. These buildings elements were then transported to the site. Here you see an exterior of this facade. I'm going to quickly show you how we designed this facade. Basically, we looked at this building, which was kind of pre-given as a container, which we then filled with these kind of overscale abstracted spheres, which of course can be looked at as grapes. They're about 3 meters in diameter in real. So we got this really compact compound of spheres. Then we looked at this volume of spheres from the 4 facade sides and actually transported this information, this kind of virtual texture onto the rotation of the bricks, of each individual brick. So kind of image information is planar, but it's also generated from a spatial configuration, so you'd see the same kind of sphere from 2 sides if you look at an at an angle situation. If you come close, then this kind of very image-like quality of the far view dissolves, and you get a more kind of dynamic field impression. And that's something which we particularly like, that it's not actually on making images and producing images, which always stay the same. So very much dependent on your distance, on the sun, on the position of the sun, the weather, and so on. Actually, the appearance of this facade changes. For the interior, you get the same sense. It actually only worked because we moved the stones so close together that when you rotate the stones, you actually close the gap of light between them. If you just made them 2 centimeters more apart, then you always get light through the stones, and the difference is too small to actually see it. So the physical always plays into this architectural reality.
Martin? Martin? Post 25 ist wieder frei. Das ist richtig, das will ich ja nicht einmal aufkommen.
the last project, it's the last project of the lecture, but it's also the last project we are working on right now at ETH is called foam. We use polyurethane foam to build additively built structures. Polyurethane is a two-component material that I mean we were using it in we used it in the Pavilion for the facade 6 years ago. It has the property, you see it here in this glass, to expand. So when it comes together, it's liquid, it's two-component. When the two components come together, they react and then they expand, so they augment their volume. Everything happens through this machine. It's a very dirty process, but kind of it was the only material that allowed such an experiment to deal with material that you can add on and it changes its consistency. We had to borrow this from a contractor and then to connect it to the robot. The only manipulation is the contractor is doing things by hand, and we do it with the robot controlling the process with data. The whole thing is still very dirty because the machine is old and complex. It broke down every 2 days, and we had to. But we suddenly got this process under control. At least being able to start the coming out of the material, to move the robot on a certain path and speed, and then to stop it again. Now, what you see here is a very simple grid. It's slightly manipulated, but it's a very simple grid. It's geometry, and the robot is controlled by geometry.
Schön, gut.
Okay, it moves around. This is the outcome of this geometry of this grid. This is the interesting point. I mean, this is construction at this purest level. I mean, construction is always a process that unfolds in time. The brick wall we have seen before, you could not start to build it from the top right side and then go down. You can do this with data, you can do this in the computer, but in physical reality it doesn't work. Now the brick wall is somehow, we are confident with this technology, would never think about starting the wrong way around doing it. Plus the predictability of the process is very high. This means we can describe the outcome with geometry and then just have to make sure that the person that builds it knows about it. He has to start from the first row and then go up. Here with this process with a material that changes its consistency, form and volume while building, the concentration on time passing between the different steps is crucial. And the whole potential of what you can do with it lies into the understanding of this of time passing while constructing. So we see it here. Of course, the grid is still there, but the robot needs an information. For example, the first information is where to start and where to end. how fast to proceed. And dependently on how we set, as designer, we set those parameters, we get a completely different result. This can be have different structure property, different surface properties, and will look completely different. So it's about this tension between the geometry that we cannot avoid, because the geometry is numbers, is precise numbers, and the robot reads numbers. It's the only thing it can do, and the result on the other side. So we see geometry is an important part, but it's just one part of the process that is needed to in the end, have architecture. I will quickly show a range of works done by students, starting from geometrical analysis, or I mean design approaches, and then the machine that does something that doesn't look like the lines they had in the beginning. It was amazing. The first review we had, midterm review, we were late as usual by with the engineering of the process, so they spent a couple of weeks thinking or talking about geometry and how the whole thing would be and what the result would be. And when they first got the results, they were all deceived. And they started to justify themselves in front of us, saying we didn't want to do this and we don't like it. And so at a certain point of this discussion, somebody asked questioned the line of thinking of the whole discussion, because he said it's like the table. The first moment you don't know if you like it or not, and why you would like it or not. But what is sure is that you would not have designed it, because you cannot design it. And that if you understand or start to understand why something happens and why something like looks like this, and reintegrate this know-how into your design intent, so into geometry you are starting with, then you start to get control on the whole process. It's a very special aesthetic. And what is interesting is that this is a pure additive process. I mean, the material is there where we want it to be and where it has to be. Plus, there is a certain degree of I wouldn't say freedom, it's a lack of control caused by the complexity. I mean, it's a fluid. It goes just in a certain set of tolerance. It goes just somewhere. But this then is an aesthetic question. So what means control? What is perfection in the result? Is a cultural question also that is connected to the technology we use to produce things that shape somehow our feeling about perfection, about being in control of material, of processes. And what's interesting too is that we tried a couple of times with some of those strange products. The process can be repeated. So if you run the same file with the same data, with the same material, with the same temperature, with the same speeds, you get, and this is astonishing, pretty much the same element. So that you would not, of course it's not identical, but you would not distinguish it. You could switch them and you cannot tell which one is which one. Always cause and effect. This is done by two. So the process is run in two steps. The first defines kind of zones, and in the second steps, those points are filled up with materials that then pushes against this boundary, this first physical boundaries, and grows it more into height than it would otherwise. This is apparently completely chaotic, but you can reproduce this. We did 2 of this one, not believing that it would look the same, but it was the same. It's just a degree of complexity I cannot read anymore. Okay, then in an elective studio that just finished 2 weeks ago, we wanted to find out how all this investigation that were conducted pretty much two-dimensionally could be kind of extruded into architectural dimensions. So we wanted to produce panels, acoustic diffuser, and there is a constraint, there is a physical constraint. If you want to do diffusion, you have to create spaces or structure that are at least 20 to 40 centimeter depth, because the sound waves have to be reflected into it. I will now interrupt this and go on. These were the results. Suddenly these things that were panels in the beginning became acoustic elements. I mean, there was a whole study done. I mean, we did measurements, interviews to find out. Those are kind of audiovisual products because they are defined by rules that are not visible, but the result is extremely dominant and visible. Creating those differentiated chambers. I mean, diffusion is all about creating chambers that will send back the audio signal, the wave, but not in the same wave and not in way and not in the same time, so that the effect of diffusion is created. And what is extremely interesting in this, for example, now in this project, is that by being produced additively, it has, I mean, the geometry is very banal. It's just circles overlapped. The fact that they overlapped by the law of this material creates differences in height. So you have, if you look at this, you have a classical extrusion design. So it's two-dimensional, extruded. This is not just a principle in design, but it's more a technological principle. You have profiles that are extruded, so in endless manner, and then cut. And you know this. But if the extrusion now is modulated in height, like here, as soon as you move out of the point of focus, this very clear, very pure geometry collapses into a something that is different, something in a landscape or in a much more complex product. Then you have the third level, is the level of detail when you go into the structure itself. We had it before, the special. This was a second project. But the students, I mean, they were experimenting, they were building during the day and then making interviews and listening to music on a very high-end hi-fi and boxes. And in the beginning they had, I mean, it's interesting, they had problems with this special aesthetic that of course is kind of challenging your perception. And in the end of the 4 weeks they were completely at ease in this room, cozy. I think that's it. Thank you very much for...
Thank you. Yeah.
Chain the effect. I mean, this will be another lecture. I mean, what interested us was that acoustics is, at least at our school, no topic at all. Acoustic is a property that generates acoustic property of a space that really influences the way we perceive and understand spaces. And in my education at ETH, acoustic was noise. And noise is something that has to be dealt with, solved. It's thinking in the category of problems. And we found out that this was a special, we got to know a person that works in the field, does electroacoustics, and he started to introduce us into the perception of how you can change space, dramatically change the perception of spaces by considering how sound may move around. This is a geometrical issue, it's a structural geometrical issue.
Do you have catalog of future experiments?
If you would like to do.
Yeah. I mean, for example, thermal treatments, which is neither additive nor subtractive, but you differentially heat surfaces and high volume materials and properties.
We do not have
Although the idea of setting students with a big flame on a robot, it's a special kind.
That's
Probably then you can use metal plus materials that would expand or slump.
that will be very interesting. I think our approach is very project driven, so we try to always go as far as we can still produce it, kind of to these limits within a given scope. And I think for the moment, being our main scope is additive, because it's such a huge field. if we add on all other possibilities, it's just, I mean,
Can you change the nozzle size?
of course, yeah.
Like a router, when it docks from a toolpath.
Change the drill bit, yeah.
Change the nozzle size in the middle of the nozzle.
Of course, you could do it. This machine doesn't do it, but I mean, it's all. That's the nice thing about the robot. You control the data. On the other hand, you build